I've been one of the brightest young men we've had here as an integral part of the physics and engineering department in the last 10 years. Because of his love for music, he's been mixing his expertise in the area with background in engineering with excellent results. This senior thesis is yet another example of using his rich background to develop something unique and well needed in the consumer market. So his talk is entitled 7-Band Portable Equalizer. So this is with great pleasure that we welcome Mr. Preble to the journey of research analysis.
Thank you very much for that great introduction. Actually, my name is Preble. I'm going to be presenting about my portable equalizer design. Before we really dive into the presentation, just want to set the mood with a little bit of music right now. Just settle us in a little bit. Oh, it's hold on. Wait.
It's supposed to settle us in.
Yeah, no, that sounds awful. Hold on. Let me find something a little bit better. All right. No, hold on. I'm gonna try. What about the? All right. Well, I'm a little bit off on all of these, and I think it's a little bit obvious that it should sound more like this. So one of those sounds better than the others. Why does it sound better? We talk about what we like in that. We say it's balanced. We'll say that the sound is more balanced. In the other one, we had too many lows, too many highs. One really ugly frequency was pushed up too high in the third one. But when we say that we like something balanced, we're actually talking about, let's see if this will work for me. Okay, we're not quite there yet. We're talking about the frequencies. We're talking about the equalization of our music and how we'd like to be able to control that to make it sound more appealing to us. So if we're designing a system that will allow us to do this, we're going to want to take in an audio signal. We'll want to take in that song, split it into the different parts. If we want to isolate the bass, if we want to isolate the treble, if we want to find these frequencies in between that we want to be able to influence, we want to be able to control it. And then we want to output this modified audio signal at a usable level so that we can pass it on to speakers in your car, if you have a pair of computer speakers. And the kicker for this system is that we're aiming for something compact, something battery operated, something portable. If I want to bring this thing with me in my car and plug my iPod into it before it goes into my car speakers, it gives me much more control than on average your car would have a bass and a treble option. But other than that, you're kind of out of luck. So if we're looking to accomplish this, we're going to talk about the frequencies. The frequency is the rate at which a vibration occurs to constitute a wave. Trying to show what that looks like a little bit more. In terms of audio, we're looking at the compression and rarefaction of air particles. Basically, particles moving back and forth, creating different levels of pressure. If we represent it in a more sinusoidal model, you see the peaks and troughs. If we look at a line in the middle here, this being the norm, we'll see it pushing far to one way, bouncing back to the other side. And the rate at which this occurs is what we're going to call the frequency. Now, what frequencies do we care about? All the sounds that we hear can be divided up into different ranges of frequency. So in one of the example songs, you heard that all of the low end was coming through. It was very muffled. You couldn't hear any of the high end. We are looking more around this area, which focuses on bass and sub-bass and kick drums. It's quite at the lower end of human hearing. A lot, like some of the low end from guitars can come into there. Bass guitar would be right around that range. And that's what you could hear when all we allowed to pass through was the low ends. Versus the high end towards like 10 to 20 kilohertz. We'll find the higher part of snare ranges. We will run into a lot of sounds that just contribute to the brightness of the sounds we're looking for. In human hearing, down here at the bottom, roughly 40 hertz to 20,000 hertz, approximately. It's different for males and females. Individuals can hear differently. But these are the ranges that we'd like to focus on. If we're going to break up sound into different ranges that we can control, we want to look at these different ranges for each one of these different parts of sound. So getting into what we have to do in this system, we want to receive an audio input. We want to break that input into the different frequencies based on these groupings that we've made in this slide. We want to take that signal, modify it, and output an amplified version of that signal so that it's usable to other audio devices. And like I said, we're going to put that out. First thing we need to do, seems inconsequential, but we need to receive the audio signal. For this, we're going to be using 3.5 millimeter auxiliary input jack. And this you'd know much better as a headphone cable. That's the size that we're looking to take in. If you have a phone with a headphone port on it, this is the kind of input that you would be using. For this, you'll see on the back here, we have 3 pins. That is one for the left ear, one for the right ear, and one for the ground, which represents the normalizing line in the middle of the signal. Next step we want to do, and this is probably the biggest part of the equalizer, is to filter out these frequencies. We want to filter the signal into several bands based on frequency, allow them to be controlled independently by a variable resistance to drop voltage as the user dictates. And then we want to take these separate bands that we've created, that we have controlled, and bring them back together into one audio signal. So what's that going to look like? We're going to accomplish this with bandpass filters. They allow only frequencies within a certain range to pass. The rest are met with a great resistance, which will drop the voltage of any unwanted frequencies. And if you look at this diagram here, I wish you could see that a little bit better, but these are what we call the cutoff frequencies. They're basically the outsides of our acceptable range of frequencies. Everything past them will start to drop off sharply, this representing the amount of signal going through for a given range of frequencies on the x-axis right there. If we will look at the structure of a bandpass filter, which you see over here, if you can see that line straight down the middle, it actually breaks it up into 2 parts, the high-pass filter and the low-pass filter. The high-pass filter is what's going to stop everything to the left of this cutoff right here. When I say high pass, I'm saying it allows everything in this direction to pass through. The low pass coming right after that takes what the high pass gives it and cuts it off at the other cutoff point, allowing only things below its cutoff to pass through. So when you combine the two, we get one behavior of one filter and one behavior of the other, closing in the band that we're interested in. For this design, we're going to need to use several of these, one for each of the different bands that we're interested in isolating in the audio signal. So controlling the signal. If you hear a sound and you want to turn it up immediately, it's too quiet, what you really want to do is to increase the amplitude of the signal. When we're representing audio signals in a circuit, we like to say that this is represented by the voltage. If a high voltage signal is passing through in an audio signal, it's going to be very loud. Low voltage will be very quiet. And the way that we can control this, the way that we can control this is by using a variable resistance, a potentiometer, a knob on the front, which when you change it will change the resistance that is being presented in this circuit. The greater the resistance, the less voltage that will be allowed to pass through. And if we implement one of these directly after filtering out all the other unwanted frequencies, then we are limiting the amplitude of only the frequencies in the band that we have selected. That is to say, I could take just one range, let's say 1.5 to 2.5 kilohertz. I could take out every other frequency outside of that range with a bandpass filter. And then from there, limit how much of that specific band is passing through using a variable resistor potentiometer. So the signal amplification is the next step in our system here. The goal is to use a non-inverting op-amp configuration to increase the gain of the signal and to allow the user to control the master output of this system. So turn up for what? Why are we doing this? We had an audio signal that came in. Why does it need to be louder when it goes out? I didn't want the signal to be louder. I just wanted to control how it sounded. The problem is that we're using all passive technology up to this point. The bandpass filter that I showed earlier does not need any voltage to operate, but that means that all that it's doing is presenting resistance to the audio signal that we had. When all that you're doing is presenting resistance, all that you can do is drop the voltage. And now you're stuck with a signal that is far quieter than what you put in. Say that I'm taking a pie. I'm cutting it up into 6 slices. These are my different bands. I take those slices apart and I start to nibble away at each one of them. I nibble away until just as much pie as I want is left. When I put them back together, I'm left with less than 1 pie. So I need to amplify my pie in order to have a full one at the end. I think that's how food works. So for the amplification, I'm going to be using an op-amp, operational amplifier. Set in this configuration, it's called a non-inverting op-amp. The reason a non-inverting op-amp is important is because I don't want to mess with my audio signal. I don't want to change it. An inverting op-amp would present a negative gain. A negative gain meaning that where I might have had a peak before, I'll have a trough. It means that I'm changing my audio signal, which is in a way that is not the goal of this system. I want to manipulate what frequencies can pass through. I do not want to invert my signal. The gain of this system, which is the ratio of what's being put into the system versus what's being put out, is described right here. If you'll notice, it's dictated entirely by these 2 resistors down at the bottom. I can choose these values in order to dictate the gain of the system, but there is a limit. At the end, you see that it's always +1. At the end of this amplification, the lowest gain that I can have in this system is 1. That means that at the very least, I'm getting out exactly 1 times as much as I put in. The problem with introducing a variable resistor as either one of these, while yes, it would allow you to control the gain, it would never allow you to lower it past 1-for-1 ratio. Whereas I thought that's a pretty useless design. Say that I wanted to turn my stereo down all the way, and instead I'm stuck at a certain level where you will always have sound leaking through. It's a little bit of an annoyance, so I thought instead what would be best is to allow this amplification circuit to go through, these 2 resistor values be fixed so I have a constant gain ratio that's being put through this amplifier, and then at the end of it all, put a variable resistor out here around the output of that amplification. So then I could present as much resistance as I wanted on the tail end of it, allowing it to drop the voltage below what I'd normally be able to through this amplifier. It just allows a more complete rejection of that voltage. Outputting the audio signal, we're not reinventing anything right here. It's the same 3.5 millimeter audio jack that we used for taking in our signal. What do we have here? Hearing double. Now, one thing that I have not addressed to this point is the fact that all of the audio signals that we commonly hear are in stereo. We have 1 wire for our left ear and 1 wire for our right ear. And these are not always the same signal. They're often close, but they're not always the same. So when I'm dealing with processing these kinds of signals, I can't treat them as the same signal. They must be treated as separate, or else, when I combine them, these signals can cause interference with one another. Say that there was a trough in one place at the same time there's a peak in the other. Those 2 signals would cancel out. So even if they're slightly out of phase with each other, we could get a signal that's mostly canceled. So in order to keep these signals separate, we need to deal with the way that we're separating them out. with the bandpass filters. I can't use the same bandpass filter for the right ear and the left ear. I have to create two separate filters having the same bandwidth that will separate out these frequencies. When I'm controlling how much of the voltage passes through, I can't put them through the same potentiometer. They need to be handled independently so that they will not interfere with each other. I actually have a special type of potentiometer for this. It's called a stereo potentiometer. It basically will control two signals simultaneously, presenting the same resistance to both, which is very important because if I tried to use two separate potentiometers, in theory you could then control the equalization completely separate on one ear from the other. It might sound cool, but in the end it would be kind of inconvenient. Say that you're trying to get the same sound in both ears, you'd be constantly messing with knobs trying to figure out how to get your music to sound the same. So, very important that these stereo signals are kept separate. In every stage, we need to treat them as separate signals. Even to the amplification stage, I use two op amps in order to amplify the signals and then output them to that same left and right pin over there. So, all right, so let's talk about actually building this. The first problem that I really ran into as far as amplification goes is the op amp that I was trying to use. A very general model of op amp, it's great for learning the circuits, is a 741 model. But I quickly found out that the 741 is nowhere near ideal for treating audio signals. It presents a lot of noise. The signal that you get through is extremely gargled. Everything seems like a good idea in theory right up until the point where you try to listen to it. It sounds awful. I did research on this, tried to figure out if there are any op amps that were more commonly used for audio applications, and I found the NE5532, which is a dual op amp, meaning that I can use one integrated circuit chip and have it be both of the op amps that I need for my system. Also, this model is much better for treating audio signals. It generates less noise. So what was the next one? The initial filter designs. I started these filter designs probably back in November. I calculated the values out, I put them together, had them all on a breadboard, and I thought, this is going to be great. I ran an audio through it, and the signal all passed through, and I thought, awesome. I started to get to the point where I would be able to manipulate these, and I thought, oh, well, I should probably test these with an oscilloscope. Basically what I could do is I could take a set frequency, say that I wanted 1 kilohertz, and I could run it through a filter, and I could measure the response of that filter by gauging how much of the signal had passed through. Upon doing this, and testing at various frequencies for the filters to kind of determine where their bandwidth was, I figured out that some of the values for cutoff points for these bandpass filters were well outside the range of human hearing. A little bit different than my calculated values. I was getting around 23 kilohertz, for example, which is something probably only a dog could hear. So I found that these values were drastically off. I went back to the beginning and had to recalculate all my values for filters, start from the bottom and build up again, testing as I built this time to make sure that I didn't have any obscene cutoff points. Like I said, I used the function generator and oscilloscope to test and confirm the bandwidth of each of these filters. And then, no. Making it last. This is kind of one of the last steps. After designing all the filters, I had gone into, put them into a printed circuit board. This printed circuit board was not special designed. A lot of what would I say, like computer chips and that kind of stuff. They print a circuit board custom for the purpose that they need. This is a very general PCB, which actually mimics a breadboard for those of you who know what that is. It basically allows a lot of basic functions to be implemented, gives you a few different points to create nodes at. Pretty helpful, but it also means that when you look at this and you see all the silver dots all over it, if any of those dots are touching in the wrong place, it could short the circuit out instantly. So working with it was a little bit like heart surgery, from what I know of heart surgery. But it was stressful. That's what I'm trying to say. But in the end, I got a, if you see like my thumb for scale right there, that one board housed, if you include each high and low pass as separate filters, there are 20 different filters on that one circuit right there. Being 7 band passes, or 4 band passes, 1 high pass, 1 low pass, for each ear, the left and right audio signal. So it was great. Holding that thing in my hand, I thought, this is great. My project is done. I got all these signals filtered out just the way I want. The bandwidth is behaving just the way I thought it would, until I went through, tried to connect the potentiometers and read the values that were presented to me there. I soon discovered that somewhere in between soldering all this together and soldering the potentiometers on, I had lost functionality in around 1/3 to 1/2 of the filters that I had put on my board. My design had effectively gone down the drain in a very short amount of time. What I did instead, and I believe this is actually a good way to look at it real quick. What's right here is 7 different filters. A low pass design, and high pass design, and you'll see a combination of each of them in the band pass filter design that I had showed earlier. This would be the left ear in this case, and not including those, the right ear over here. So like I said, each of these signals has to be processed completely independently. I had a completely separate set of filters for each one of these signals, handled by, there's no nifty way to represent stereo potentiometers, but that's what this is representing. Passed on to 2 separate op amps with fixed resistance, variable resistance applied to the output of those op amps, and then output through a 3.5 millimeter jack. Hopefully this shows a little bit more how all the pieces fit together in the end, ideally. And the finished product, so to preface this, after learning that none of my filters really worked, I went back to the beginning and tried to show at least the functionality of what the circuit is to accomplish, and that is to isolate bands, to manipulate them at will, and to output them at a usable level. So the demonstration I have here is actually not on a printed circuit board. It is on a breadboard, but I will at least be able to show you manipulating a signal. Again, this is testing using a arbitrary function generator read by an oscilloscope after passing through the circuit. I should be able to, there. Sorry, it's a little skinny. It was taken on a phone, so this is, hopefully this will help. It would be way better if I plugged in the audio to here.
All right, one more video demonstration here. Now, input is going to be a function generator right here. Just putting it sideways, you can see it on the screen. Right now, I'm just putting in a signal 80 hertz, so the only thing that should be able to affect it will be our first filter right here. So see when I turn that up, we're getting more signal in, or out of this circuit.
This is where we're supposed to be reading right there. It's a little hard to see.
But if I go over to, say, the next one up, it does not have any effect on it. It's pretty far outside of this range. So we go back to this one, and if we increase our signal, let's say I want to go to 3,000, this makes it see a little bit better here. Now, we can play around with the next band passes. Now we're inside this effective range, so the potentiometer can affect these frequencies.
All right, that was a quick demonstration. What I was trying to show was that while a signal being passed through one band of frequencies can be affected by one bandpass filter. It was filtered out, separated from the rest of the signal, and manipulated independently. It could not be manipulated by the X out of this. It couldn't be manipulated by the different band passes whose range was far outside of what that value was. If we look here, I can try to show you why that would happen. These are the values that I took off of the printed circuit board, the full 7-band, before it fell apart. I did get some data out of it. So for an example, if I were passing through a value of frequency that was right about here, this blue, this dark blue right here, would be the only, maybe not the only, that has a little overlap here with the pink one, but compared to all the other bands, it would not have any kind of significant effect on a signal that was being passed through the middle of this band pass's range. So what I was trying to show was that once I moved the signal, the frequency, further out this way, instead now we're in the area where the light blue filter can have an effect on that signal.
Real data?
Yeah.
How did you get it?
Okay, this was done using the oscilloscope and arbitrary function generator. What I would try to do, I knew in advance the cutoff areas that I was aiming for. So I would start by putting, say, a signal of 10 hertz into the circuit with the function generator and reading the output with the oscilloscope. I could then have the oscilloscope set to like print out the voltage that was being read there. So I would move it up by another 10 hertz, take a value, move it up another 10 hertz, take a value. And using that data, we kind of plotted. You can't even really see it because it goes 1 to 100 on a scale of 0 to 25,000 hertz. So it's kind of the red line that you see right along the axis there. There are different ways to display frequencies like this. Really follows more of a logarithmic scale. So if we were viewing it like that, these bands would seem a little bit more equal. The reason that it looks like these two are dominating so much of the graph is because of the way that frequencies work in terms of octaves. Each of these filters represents about an octave to 2 octaves of, like you would say, notes on a piano. If I go C to the next C on the piano to the one after that, it's 2 octaves apart. The way that that's represented in frequency, though, the distance that you have to bridge is not the same 12 keys every time. It is double the frequency every time you want to go up 1 octave. So when I say that from 5,000 to 10,000 hertz, on a piano, that's the same size jump as 100 to 200 hertz. So that's why you're seeing all the bands here scrunched so far over to the left side. They're actually pretty similar in the, I'd just call it the domain of frequency that they control. So basically, to get back to the original question there, these graphs are made up of sending through a signal, reading the result off, moving up an increment, and repeatedly testing these filters to see how they responded to a constant signal being passed through them. I'm looking at these a little bit more in depth now. It's scaled so that you can see how these things slope. This one is the low pass filter. It's supposed to only let through things below 100, or 80 actually. So 80 would be right about there. So this is what we're mainly focusing on, and after that it trails off down this way. So that by the time we're further on, we're getting way less of the low signal through there. The next band pass is focusing on 100 to 500 hertz. We have 100 down this way, 500 over here. We'll notice that there's a bit of a plateau behavior around the top there, and this is the band that we're hoping to target we're hoping to manipulate using a variable resistance after passing through this filter. Moving on to 500 to 1000 hertz, 500 hertz to 1 kilohertz. We have the cutoffs a lot closer here. And the plateau starts to kind of dip down before we get to 1000, but we're pretty close to an effective range there. Bandpass 3, this one targets 1500 to 2000. I think 1500 should be right. Yeah, right about there. That's 1400 and 1600 if you can't read that. And 2000. This one does cut off a little bit early. Some of these values were a little further off than expected. But another thing to keep in mind is that the cutoff is generally measured from what we call a 3 decibel down point. If you turn that into a multiple, it would be 0.707 of the original maximum signal. That's how far down we're looking to drop the voltage before we say this is the end of what we would call our effective bandpass region. Moving on, we have 5,000 to 10,000. Again, 5,000 between 4,000 and 6,000 right there, and 10,000 over to the side this way. That's the plateau behavior we're looking for. And then our high-pass filter. This is my favorite graph. It looks like a nice big wave. I was originally hoping to hit it around 16 kilohertz. This one picked up more around 18. At this point, that's probably less difference than a few keys on a piano. So I took that as an acceptable result in this case. It still controls a very similar range and frequency. A lot to do with just the brightness. There's no one instrument that its primary domain is this high. Now we get to, this is probably going to be the easiest part to understand. The part I like the best is we're going to listen to what a signal sounds like when it's being passed through these bands. This is just a video of playing around with an audio signal and manipulating it using these variable resistors.
My name is Chris Preble, and this is a video demonstration for recording sound on this computer over here, along that wire, into this 3.5 millimeter jack, processed by the equalizer, and then output through this little speaker over here. So let's get started. Make it sound muffled, double, you turn up the bass all the way, this other stuff here. And there we go.
All right, so what we were looking at there was how this actually will change an audio signal. I think it's always a little easier to understand what's being passed through, what's being manipulated if you can hear it. That's just me knowing music, talking, trying. So we've got that video demonstration. All right, it looks like we're approaching the end here. I'd first and foremost like to thank Dr. Cornley, the Physics and Engineering Department. When I first came here, I was no idea what I was going to do. I was an undecided major, and I thought, oh, what could I jump into now that I could possibly be happy with and spend the next 3 years doing? And my first year in the engineering department, coming in knowing nothing, was actually Dr. Cornley's first year at the school as well. And he has definitely made me understand better and enjoy a lot more than I thought I would a lot of the engineering concepts that I've gone through here. So I'd like to thank him a lot, and the rest of the physics and engineering department. I'd also like to thank my classmates for, in some of these engineering classes, for very long and sometimes productive nights studying. But yeah, I'd like to thank my parents for coming down here and hearing this speech. Yeah, every one of those people deserve a round of applause. So, that being said, I will open it up to questions. Right there? All right. Any questions on the system? Anything that I said today? Yes, sir.
Is this all digital processing, or is there any analog conversion?
There is no digital processing. Everything that's accomplished is done by RC circuits, all resistors and capacitors, using the natural frequency responses of capacitors. Basically, the fact that they resist the change in voltage in any circuit means that while the audio signal is trying to shift positive to negative, depending on the resistance presented there, and the change in voltage that the signal is attempting, it will actually restrict that a lot, which is how you see some of the cutoff behavior at the edge of the band passes. And by inverting the position of the resistors and capacitors, you get the opposite effect, whereas one will be a low pass, the other is a high pass. That's how we achieve the different ones. Anyone else? Yeah?
So if you used an inverting op amp, would it give a different sound to the audio signal, essentially?
In all practicality, it might not be easy to notice, to be honest. Because if you want to start talking Newtonian, for every action there is an equal and opposite reaction. If I'm going to go all the way back to where I showed this wave right here, completely uniform. If I flipped it where the peaks are troughs and the troughs are peaks, you wouldn't notice a thing. It would sound the exact same. The thing with an audio signal is they don't look like that. That's one note out of a million different tones that are coming through at the same time, combined into this audio signal. So when you invert that and you realize that it's constantly changing, an inversion could actually have a little bit more of an effect on that signal. But again, we're talking about a difference in a span of maybe a thousandth of a second in some cases. And way above that once you get to the higher end of 20,000 hertz. It's 20,000 vibrations in 1 second. When you get to inverting something at that speed, it would be pretty hard for our ears to pick up, but better safe than sorry. I'd rather keep the original orientation of the audio signal intact. Anything else?
Back to the beginning in your justification for doing this, I guess I'm not quite sure, because the professionals balance the sounds originally.
Right.
So is it because you personally like something different, or is it the environment you're trying to have equalizers for that too?
Oh, you're right. There are a lot of professionals who are paid a significant amount of money to make these songs sound good before they ever hit our ears. The problem is, and I think this is a huge lesson of engineering as well, that's the ideal world, and we live in the real world, where my speakers are not of the highest quality. I go into my car stereo, and let's say the natural tendency of that system is to play bass frequencies higher than treble frequencies. Well, I still appreciate some of the treble frequencies and would like some control over that. So by compensating, by altering the signal before it ever hits those speakers, I can make those speakers, which had at first sound undesirable, sound more balanced and more level. And especially if you get to the level of small computer speakers, a lot of these things that applications that we might already use frequently, we just wish we had a little more control over. That's the idea for the application of this product.
So what did you find in your patent search at the beginning of this project on this class of equalizers?
Right. Searching for patents and stuff, there are many different equalizers out there, inside stereos, Computers will come with digital equalization settings on them most of the time. The big thing that I thought would make this system more convenient is the idea of being battery operated, of being portable and convenient to move, because I'm not going to bring my entire stereo system with me when I'm driving in my car down to the store and I want to listen to some music on the way. But if I have a small convenient unit that I can just keep in the little cup holder on the side, that it helps me adjust these different frequencies, then I'm much more likely to use that. It's much more convenient as a design in that sense. So another reason I used the passive components, which I did not mention earlier, is that by keeping down the amount of power that I use in each filter, the only place where I need extra external power at all is in the final amplification stage. So it takes away from a lot of the power that I would be using in filtering stages and lets me focus on only using a limited amount of power in the amplification stage, which isolates the use of energy, and this helps keep it a little more compact. The filtering stages are also nowhere near as big. It would have taken several IC chips in order to complete those filtering stages, and at that point there would be no way for me to fit it on one printed circuit board like I did there.
Go back to the plot where you had all of your filters on one.
Yep. Oh, we're
That's
gonna.
the other way. Right there.
Oh.
There, yeah.
There.
So you talked a little bit about the 3D point, but
Yep.
I guess I have to think about this a little bit, because you want to look at the power versus the magnitude of the signal, but it looks like you actually have sort of created dead spots too.
Right.
Say, you know. So.
There are some dead spots in this. A lot of that is what the reasoning behind that is more, and I guess this is not something that you can always plan on, but them compensating each other. See, as this one is going down and would continue that way, this one is also decreasing, but the combined signal at that point would be additive and put it about here. So where one is low, the other is high, but these midpoints together kind of help to bridge their own gaps in that sense.
So you thought about that as you were picking the...
Yeah, if I had put these too far apart, we would have started to run into larger dead spots where it would affect a wider range of frequencies. But even assuming that from, what would this be, about 1,300, no, not even, probably 12.5 kilohertz to maybe 13.5 kilohertz. Again, it's like this side of the graph is very zoomed in and this part is very zoomed out, so it's a little hard to tell by the scaling, but we're looking about maybe between, wow, so that would be, yeah, probably not even a whole step on a piano is the range of frequencies that we're looking at right there.
The other thing I think that you probably forgot to mention is, I think that when you try to be too cute with getting these bands filled out, you got a problem there, remember?
Right.
Take one of these.
Yeah, actually, when I went back to redesign the filter after finding out that my cutoff values were outside of the range of human hearing, I went back and started to look at where I'm placing these cutoff values, and especially down towards the places where a few hertz is just like hair splitting. I realized that setting goals, like if we go back to the beginning, I think that you can see one of the original goals was to have, right, so I did change it on here as well. The original said 100 to 200 and 200 to 500, which is good because it is an octave. It's 100 to 200 is an octave, 200 to 500 is about an octave and a half. But in the end, when I try to create cutoff filters that are cutoff frequencies on these different filters, it's hard enough to place them exactly where they are that I wouldn't have either massive overlap or the band width of the actual, so either the 200 would get too far into the 200 to 500, or I pull it back too far, and now the high pass is interfering with the low pass. There's no real bandwidth on my 100 to 200.
So because he's using analog designs, and there are tolerances on both the resistors and capacitors that you cannot predict beforehand. So you put them in, you say, oh, this is supposed to be at 10 hertz. When you look at it, it's 9.6.
Right.
And so if you start being too cute, then you get in more trouble.
Right. And that's the reason I combined to make a 100 to 500 hertz. I think that should be one of the largest octave gaps that I have here. I think it is the largest, spanning 2.5 octaves. But in that low range, most of all that it would be processing is bass guitar, the low end of a piano, maybe like the last string of a normal guitar.
The other thing is if you start using fancy processing, like Jeff was saying, then you need a whole bunch of power. And the purpose of the design is to do something that you don't need power. So it's kind of juggling act.
Yep. And when designing this system, I know that it's kind of a sacrifice that I had to make, but I knew when I was designing it, this is not a system that you will find in some recording studio where they are top of the line, like trying to create the best possible sound. This is a device for after-the-fact tweaks that will improve in existing systems, making it sound a little bit better. It's just for that little bit of color on the consumer end versus something that you would use on the professional end.
All right. Any more questions? I think we've gone way over our time here.
Yeah.
Any more questions for this speaker before we thank him for the last time? Very good.
Thank you very much.